Okay, so let's get started on the continuing discussion of electrons, fermions and bosons in one dimension. So just to summarize where we are, we started considering just free fermions in one dimension and just simplified them to just linearly dispersing from right-moving and left-moving fermions near the Fermi points. And then later on, we also added some interactions. So there's also an H int, and this could become generic forms, and we're going to explore that a bit more today. And so these are fermion fields that obey the standard commutation relations, anti-commutation relations, and here's the action. And what we established, and really we proved it for the case of free fermions, that this theory is equivalent to a boson theory, which has many different formulations. One formulation is in terms of the fields phi and theta, which obey this strange commutation relation. And the gradients of these phi's are up to factors of pi, respectively, the density and currents of the two fermions. Then in the path integral representation, you can write the strange commutation relation by this extra Berry phase type term in the action. And once you put that extra term, you can integrate out either theta and phi and get a familiar theory for phi or theta, which is just a relativistic theory of a scalar field, massless scalar field. And the power of this approach, which I also discussed last time, was that you could put in some interactions in the free fermions. And actually, at generic densities, there's only one change in the entire theory. You get these extra factors of k that appear in the action. And also, from this bosonic theory, then, since the effective interactions are so simple, you can then compute various correlation functions. For example, the fermion operators are given by these exponential so-called vertex operators of theta and phi. And among the things you can compute by just simple Gaussian integrals is, for example, the distribution function of the fermion. So you can get a relationship like, psi dagger r of x it equal times psi r of 0 at long distances. This has a behavior which I'll have to look up. I'm sorry. It goes here. It goes as mod x to the k plus 1 over k over 2. That I should have known. There we go. Yeah, okay. 1 over mod x. And when you took a Fourier transform of this, this implied that the usual momentum distribution function of n of the electrons, n of k, had a singularity at kf, which was kind of unusual. It was some power law singularity. It wasn't a discontinuity, except for the special value of k equals 1, capital K equals 1. Okay, so these are all results that we've established. Are there any questions on these results? Okay, I can see you might see that I have a swollen lip. That's from a dental appointment, but hopefully won't cause any problems in this lecture. Okay, so now we want to put in some other interactions. And usually, as we've argued, because of, generally it turns out that any sort of interaction at generic density doesn't do much other than change the value of k. And this is analogous to what we saw, for example, in the Bose Hubbard model where any sort of interaction didn't change the fact that you were superfluid unless your density was some integer multiple of the lattice spacing. And that's a similar phenomenon that you find here. But now we want to look at special densities, in particular densities like half filling. So this is what we began the discussion last time. So when you have densities like half filling, then new phenomena, new types of scattering events are allowed. These are sometimes called Umklapp events in condensed matter. So I've discovered that particle theorists always get confused the moment they see a word Umklapp in a condensed matter paper. It's really nothing complicated. It's just the effect of the periodic potential. So you have some dispersion. You have some dispersion in the Brillouin zone for your fermions. And then typically, these are your Fermi points. So all these states are occupied and the states above are empty. And if you want to conserve momentum, really generically, the only way that's possible is you can take an electron from here and scatter it to a state over there. And similarly, you can take an electron from here and scatter it to a state over here. And this way, when that scattering event occurs, the gain of momentum, no, that won't do it, has to go the other way, right? The net momentum has to not change. So the electron from here can scatter over there. So these two electrons gain equal and opposite momenta, so the net momentum change is 0. And these are the only processes that are allowed. But when you have a lattice, there are special densities under which a new type of process becomes possible. And that's a process, the Umklapp process, where two electrons, one sitting here, one, very close to this Fermi point, are able to go, to the other side. Here, these arrows are supposed to be near the Fermi points. Okay, so the net change in momentum in this process, if this is minus kf and kf, so this process net change in momentum is 4 kf, because you take two electrons and each electron is picking up momentum of kf. And so this, you might not say, doesn't conserve momentum, you're done. But in a lattice, momentum is only conserved modulo the reciprocal lattice vector. And in this language, that's simply 2 pi. So this is allowed if 4 kf is an integer multiple of 2 pi. Okay, so the simplest case is kf equals pi over 2, which you can then figure out for spinless fermions is half filling. Okay, so you try to write down an operator that can do this, which takes, as you see in this expression here, 2 left-moving electrons and converts them to 2 right-moving electrons. Fermions, I should say, since I'm not keeping track of spin. Now, of course, psi L squared is 0 because these are anti-commutators, but you can point split them a little bit. And once you point split them, in the continuum limit, you get extra powers of gradient. So naively, you would think, oh, these gradients are going to make this term very irrelevant. But they don't, because those gradients only affect the prefactor of the term that survives, and the prefactor, is whatever its value. But now this term, if you now take this expression for theta and psi L and psi right, which are somewhere here, these expressions. So no, not those. These ones here. If you take these two expressions, well, not even those, these ones. So if you take the psi r dagger psi right, psi left, that's equal to e to the 2i phi. And you have the whole thing squared. So you get e to the 4i phi, and then you get the complex conjugate because it's a Hermitian operator. You have the opposite process also allowed. And so when the dust settles, you get an operator which is unlike any operator we've met so far. It's cosine of 4 phi. So now this thing is, of course, the free field theory. This STL is just the free field theory, and you have cosine of that operator. Okay, so now we have to, we're going to take a little interlude to try to understand properties of this theory. Now, actually, I'm not going to do a complete job. I'm not quite sure maybe how you can cover it completely in the lecture, or we'll do it later in the semester. I'm not quite sure yet. I mean, in the section, how you could do it in the section. So this theory is the Sine-Gordon field theory, and it's been looked at both in the condensed matter and the field theory literature. And ultimately, it was in the condensed matter literature it was properly understood that it has a phase transition, which is now called the costless-Thouless transition. In this case, we're talking about a phase transition at 0 temperature in one spatial dimension, or 2 space-time dimensions. And as we'll see, it describes a phase transition between the Luttinger liquid and the charge density wave state with a gap. You could equally well describe a very similar theory for finite temperature phase transitions in 2 spatial dimensions. So the total number of dimensions is always 2, it's either space-time or space. So if you go to finite temperature, you don't have to consider time. It's not important at long distances. And then the equal time theory for finite temperature thermal transitions is also a costless transition in 2 dimensions. And there it describes the appearance of superfluidity in a Bose gas, for example, and many other problems with a global U1 symmetry. Essentially, any theory with a global U1 symmetry in 2 spatial dimensions is likely to undergo a costless-Thouless transition as you increase the temperature. Okay, so but I won't describe that in any detail. I just want to understand one very basic property, which was actually understood by Coleman in one of his papers, or who was a professor here. But Coleman actually missed some of the details, which so he did not get the costless-Thouless transition right. Okay. All right. So if I look at this potential, cosine phi, I can draw it here. Looks something like this. And the field phi now, is fluctuating on this potential. Okay. Field phi is running around in this potential. And you can ask, how important is this potential? So what we'll find is that depending on the value of k, if you go to long distances, 2 possible fates are possible. One fate is that the potential doesn't matter. It becomes weaker and weaker and weaker at long distances, and the field phi just keeps sliding around from minus infinity to plus infinity without caring about where the potential minima are. So we say it becomes irrelevant. It's like you're skating on some periodic ice, and it doesn't matter to you that the ice is periodic. You just skate right over it. Skate to 0. But and that's in fact what happens in the Luttinger liquid phase, because the cosine 4 phi term just disappears and you're back to the Luttinger liquid. However, there's another fate that's possible, where as you go to long distances, this potential becomes more and more steeper, and then you get trapped. You decide, you pick one of these minima and you get trapped there. Then, so you're trapped over there, and you'll sit there basically forever, and you will maybe fluctuate around in this minimum. And since there's a curvature, that fluctuation will describe a particle. It'll have a particle with a certain mass. Or you can have fluctuations where in some region of space you're here, and then you go over the hill to the next one. That's all you manage to do. And when you do that, that will be described. It's also a particle, which is sometimes called a kink, and I'll show you that, or a soliton. But these all are gapped excitations. So you get a phase with particles, soliton, or kink-like excitations. We all have an energy gap, and these are very different from the Luttinger liquid phase. But one thing you should ask before we go to any of these details is, are these distinct minima physically distinct? I mean, is there some observable which you can measure, which tells you that this minimum here is not the same as the minimum over there, and so on. So it turns out that in this particular filling, for this particular case, the minima are distinguished. Only two of them are different. The others are all pretty much the same. It's as if you're going in a circle rather than a line. And what are the why two of them? Well, one operator that you can measure is this one, psi dagger r psi left. That's nothing but the charge density wave operator, because if you look at the density at momentum 2kf, so if you take the Fourier transform of e to the I 2kfx of psi dagger x, the full density psi x, and then you just take the Fourier transform, you'll find that this is basically equivalent to psi dagger r psi l, and that from the bosonic representation is e to the minus 2I phi. So you can measure e to the 2I phi. It's an observable, even though the action has a 4I phi, 4 phi, and those are distinct, physically distinct minima with whose properties I'll describe in a minute. So this means that, when phi is equal to one minima, of course, if let's assume lambda is positive, one minima will be at, say, 0. The next minimum will be when 4 phi equals 2 pi, which is pi over 2. And the next minimum would be pi, and so on. So as far as e to the 2I phi is concerned, 0 and 2 pi are the same, but 0 and pi by 2 are not. So so this minimum, it turns out, let me put an x over there, x is the same as x, and this is y, and it's a different minimum. So there's only two independent minima, and it's as if you're breaking an Ising symmetry. So I'll draw a little picture that'll make this completely obvious in a minute. Yeah, maybe I should draw the picture now. Okay. So what we have seen is there are two independent minima. Let me just illustrate this in a even more intuitive way. Forget all this fancy stuff. Suppose I was just thinking about this. Okay, in a very naive way. So my naive understanding is that I have fermions that have filling. So they're fermions on a line, and they're half filling, and I want to form an insulator. Well, what's the insulator I can form? You can form an insulator like this, where every second side is occupied. Or you can form an insulator like this. These are both at half filling, but they're physically distinct. And this breaks the symmetry of translation. Your unit cell has doubled. Okay, and these two states are precisely the states, let's call this the state X, and this is the state Y. Of course, if you translate this two lattice spacing, you come back to the same state, and that's similar to translating phi by pi, you come back to the same state. It's not a physically distinct state. Okay, so maybe I can't resist now actually showing you what is a kink. So a kink is, say, you're sitting in the X region, or as of sitting here, I was sitting in the Y region, and you tunnel over to the X region. So that would correspond to the following situation. Here's my line. I start out in the X region. So this region is the X region. And then I miss well, okay, let me do it over here. I jump over to the B region. So I have a defect here where I have two sites that are occupied in succession. So this is an X region, this is a Y region. And if I draw as a function of space here, the value of phi, well, in the X region, phi was 0. So let's just to be dramatic, we'll put the 0 over here. And in the other region, Y was pi over 2. So I'll put that over there. So if you look at the value of phi, it's 0 over here, and then in some region over some width, it goes over there. Okay, so now it's X-like and there's Y-like, and this is the famous kink solution that you might expect for the system to settle into as an excitation above the ground state. So another beautiful thing we can now ask, what is the density in this region? What is the density of particles in this region? Well, we already know the expression for the density. The density we had learned, rho of x, is 1 over pi times gradient of phi. So what is the total density in this region? It's dx rho of x. So that's 1 over pi. The integral of grad phi gives me pi over 2 equals 1/2. So here is our famous fractionalized charges that we saw in 2 dimensions. The spin-on, for example, the E particle had fractional boson number 1/2. So here's something that has fractional fermion number 1/2. And it's very easy to understand that. I mean, if you just look at how much extra density you had to put in to create this domain wall. Well, you can see, suppose I had a second domain wall where I went back to X, and you asked how many particles I had to put to create 2 domain walls. You will see that you had to put 1 particle to create 2 domain walls. Between a configuration that was X everywhere to another configuration that was X, Y, X. You have to just add 1 particle to convert X everywhere to X, Y, X. And therefore, each domain wall carries half a particle. Okay. Now, of course, this is not strictly, fractionalization as beautiful as in 2 dimensions. It's kind of a simpler thing because it's really tied to the presence of broken symmetry and the fact that you have these X and Y regions, and it's really bound to that domain wall, or in some cases it can be bound to the edge. So that's the nature of fractionalization in 1D. You don't get true fractionalization. You get, when you have a gap phase, you only get fractionalization associated with symmetry breaking, or with edges, like in the Kitaev chain that you learned about in the section. Okay, so all of those beautiful properties are contained in this theory, and really I haven't used any properties of this theory.
Sorry.
Let me finish that sentence. So the only property I've used of this theory is that there are 2 regimes. In one regime, we can assume lambda goes to 0, and other regime where we can assume lambda is really strong, and we just look at the saddle points in the 2 regime and we understand everything I've said so far. Yes, question.
Yes, sorry. So maybe maybe a naive one, but like in this 1D fractionalization, can we think in the same language? Can we say that when we have like domain walls, it's just like a simple Ising model that basically like the same thing occurs, or is it like somehow different?
This model is pretty much you can rewrite it. It is very much an Ising model. You can write it as an Ising model. You can just, it's got a gap to everything, and then there's no, but there are more complicated. You have gapless fermions, these domain walls are 0 modes of the fermions that are also very important in topological generalization in higher dimensions. We'll be coming to some of those. But for this model, yes, you can just think of it as a domain in a 1D Ising chain. Yeah, it's really as simple as that.
I see.
However, there is, as far as the domains are concerned, however, the phase transition. So with the Ising chain, so what's the fundamental difference between if you just use Ising model? If you just use an Ising model, let's say it's an Ising ferromagnet, it has a phase transition from a ferromagnetic phase to a gap phase, a trivial phase. So there, both phases are gapped. And that's why the phase transition is described by the Ising field theory, or which turns out to be a Majorana fermion in 1+1 dimensions. However, the phase transition I'm talking about here is not described by the Ising field theory. It's described by the Kosterlitz-Thouless transition. So this theory here is a bit richer than the Ising model, and that's because what happens here is that as you approach the region where you're going to the Tomonaga-Luttinger liquid, which is a gapless phase, the Ising model doesn't have a gapless phase. the gap, to these domain walls becomes smaller and smaller and smaller, and it vanishes in a way that the other phase is gapless. So as long as you're in the broken phase, you can think of it as Ising model, but it's not correct to think of it as an Ising model as you approach the Tomonaga-Luttinger liquid. So the lambda equals 0 phase is not present in the Ising model.
I see.
Only
Okay,
the
yeah,
lambda
that,
goes
that
to
makes
infinity phase is present. Yeah.
Thank you.
Are there other questions? Okay, that was good. All right. Yes.
I remember that for different sign of lambda, there are two kind of phases, right? One is a checkerboard, the other one is a dimer.
Yes, you're right. Yes, thank you. So if you take the opposite sign of lambda, yes, you're what Hayu is making. There's another possibility. Yeah, let me take another slide to point that out. Well, yeah, I'll add that slide later. Well, maybe that page. Okay. So what Hayu is saying is that there's another way to get half filling, is to form. Well, here's our. Let me to take our sites, and they all have equal density, but the fermions or bosons are hopping back and forth. So like a valence bond or dimer phase, they're going this way and that way. So just as one fermion here, which is rattling back and forth between the two sites, and here and here and there. So this also has a twofold broken symmetry. You could put the dimers here or like this. And this phase corresponds to the opposite sign of lambda. So where is it? Yeah, if you take lambda to have the opposite sign, then the minima of cosine 4 phi will appear when 4 phi is pi or differs from pi by integer multiples of 2 pi. So basically, that's the equivalent to taking this potential here and flipping it. So if you flip it, then this point here will become a minimum. Let me call that point A. Oops, different color. So this point here would be an A. This point here would be a B, and this would again be an A. And these A, B, A correspond to these states. This is the A state, and this is the B state. So this is also can happen, and it just depends on the microscopics. When you actually work out the interaction, you actually work out, carefully from the microscopics what this coupling is. Oh, I don't know why I called it V. Okay, it should be lambda. Anyway, so you work out what comes over here, and you do the bosonization. It's kind of tedious, but and you have to get all the signs right. Then you figure out what the sign is. But both signs are allowed. The theory is perfectly stable for either sign. Thank you. Other comments? Okay, so now what I have to do is just establish what I claimed. And the main claim for this picture that I presented is that lambda has one of two possible fates. Either it flows to 0 if I go to long distances, so that I can just skate over the potential, or it flows to infinity, so I get trapped in one of the minima. Okay, so what I'm going to do is just describe the fact that there are two fates, but the calculation I'm now describing fails right near the critical point. So this calculation was, I think Coleman was one of the first to do it, and it's really very simple in the modern RG language. And the equation for lambda under renormalization group is this very simple equation here. It depends on the value of 2 minus 4k. So there's various ways of doing this. The simplest way is to just use some RG technology, which I really haven't covered in the course, but let me just quickly illustrate it. So what I do is I try to compute this 2-point correlation function, e to the phi of r, e to the I phi of 0. So I kind of computed that last time. I skipped over all the stuff about correlation functions, but let me just show you this calculation in its bare bones structure. So if you, the theory in some relativistic notation, the Lagrangian is just d mu phi squared. And you have to get all the factors of 2 pi right, which I'm not here. That will be a homework problem. And the 2-point correlation is obviously 1 over k squared, where k is a 2 momentum now. And the Fourier transform of this is right here. But this has an infrared divergence. It goes to infinity. So this seems like a meaningless thing to do. Maybe the theory is not well defined. But then when you accept the fact that what matters are not actually the value of phi, because the theory has a shift invariance, so you can shift phi by a constant, not change a thing. What matters are the differences in values of phi. So instead of looking at phi of r, phi of 0, you look at the correlator of phi of r minus phi of 0 squared. That has complete finite sense, even provided you put an UV cutoff, which you're allowed to do. It's just IR cutoffs are not allowed. So that's what this becomes, and you can take this integral and you get a log lambda of r with a coefficient here that you have to get right. Okay, so that integral gives you this. So now I want to compute this 2-point correlation. Luckily, it turns out to be precisely related to this function here. It's exponential of minus 1/2 that. And then you compute it, you get 1 over r to some power. And in this case, it's actually, we know what the power is. I hope I remember. Well, the power is worked out in the notes here. Yeah, so here I do it here. I actually compute it, and you get p squared k over 2. In this case, p is 1. Okay, so p is 1. This will be k over 2. Okay, so then the reasoning is that this seems like some correlation function in some scale invariant theory, because I take a 2-point correlation function of these operators, they always decay with the power law. So if it's a scale invariant theory, you can ask, how does, what is the scaling dimension? In other words, each of these operators, how much do you have to rescale it to establish scale invariance? Well, the rescaling power, or so-called scaling dimension of one of these, is just half the power over here. That's p squared k over 4. So then if you go back here, if you look at this term here, so this is minus lambda integral d2x, and then e to the I 4 phi plus e to the minus I 4I phi. And when you do some rescaling transformation, x goes to x over s, which will be then become e to the L. I'm sorry, I'm using a lot of RG language here. Maybe this can be covered in section if you haven't seen it before. And I think some of the earlier notes on field theory did have some discussion of this RG, but we just doing the very simplest thing here. And then the e to the 4I phi, we just computed its dimension of e to the 4I phi under rescaling was, well, you put p equals 4, it's 4k. And this tells you the dimension of x is -1. And now you just add up the dimensions here. You have dimension of x. This gives you -2. This gives you 4k. And the dimension of the whole thing, the action must always be 0. So the dimension of lambda is 2 minus 4k. And lo and behold, you get this equation here. Well, I wrote it down for general P. And now there's another way of deriving it, and I have actually given in these notes the totally, self-contained way of doing it. Even if you haven't met RG before, this is one of the simplest way to understand RG. So the idea here, you take a phi of x and decompose it into phi lesser and phi greater. Where phi lesser has Fourier components between some smaller than some cutoff lambda e to the minus L. And this has components between lambda e to the minus L and lambda. So e to the minus L will be very close to 1. So L is very close to 0. And then what you do is you integrate out all the phi greater. So to first order, this just means you look at here's the cosine term. It's in real space with phi lesser and phi greater. You just have to take the average of this for the phi lesser action. You just take the average with respect to phi lesser. Sorry, phi greater, because you're integrating on phi greater. So you just have to take the average value of this. And this we've shown what it is, e to the minus phi squared as 0, which then gives you, so that expression there, this is one more step that's not here. So expectation value of phi greater squared is just the integral from lambda e to the minus L to lambda of dk d2k over 4 pi squared times 1 over k squared. So that's just the Gaussian action for phi. Okay, then there's factors of 2 pi that are not getting read because there's a 2 pi k somewhere, something like that. But anyway, you work it out. So that you can just expand to first order and d lambda. For here, d lambda is just lambda times 1 minus e to the minus L. And this is what you get. And there, lo and behold, is your complete, well, so that's one change. And then you have to rescale coordinates. You have to rescale x. And then when you put it all together, that's your introduction to RG. And hopefully you can read that more carefully. I think it's fairly critically explained. And this is the RG flow then of lambda. So what we see here, yes.
I just have like a short technical question. Like there, this expectation value goes into exponent. So in this case, like this is like in general not true, right? So this is here because we have a Gaussian action, or how does this happen?
Well, I mean, this is this is true for any Gaussian action that this is equal to this. Yeah.
Yes.
It's true.
Okay,
but in fact, here we don't even need to do that because in the end we expand the exponential to get the 1 minus. So you could have just expanded this and done it to second order and you'd have gotten this answer. We take this exponential and we expand it anyway.
Right. But this is exact in a sense that here it's exact because the Gaussian is because the action is like the 0 is Gaussian.
It's Gaussian at lambda equals 0, so we're doing perturbation theory in lambda. So this is just some kind of first order perturbation theory in lambda to derive the RG equation. To get the full picture correct, you have to do second order perturbation theory in lambda. And then you'll find that there is also renormalization of k. We're just thinking of k as a number given to you once and for all, but it also gets renormalized. And that renormalization of k becomes important precisely at the point where this goes to 0, which is the location of the phase transition. But I will not discuss that here. Okay, so then let's just go back here. So for this particular problem, we see that k equals 1/2, not the free Fermi point, but k equals 1/2. K equals 1 was the free Fermi point, is the critical point for this phase transition, where for k less than 1/2, there's a flow to large lambda, and we instability to the mod insulator I just described, either the dimer phase or the charge instability state, which I've already discussed, I guess. And it has these kink excitations with charge 1/2. Yeah, so that's, and for k greater than 1/2, lambda goes to 0 and you're back to a Luttinger liquid. So you have a very simple phase diagram. So let me try to draw the phase diagram here. So this is the value of k, and let's say this is lambda. So as a function of lambda and k, which are the two coupling constants in our field theory, what we've learned, I always forget which way it goes. For k greater than 1/2, this goes back to lambda equals 0. So this point is 1/2, and that's actually an exact result. The critical point is that k equals 1/2. Then here, in blue or in green, let's say, you have a phase which is the Luttinger liquid. Okay, and what we've learned that the flow of the coupling the flow of the coupling here is vertically downwards. It just flows down to 0 to either direction. Okay. Then what about k less than 1/2? It's relevant. So now the coupling, the flow is the opposite direction. Take one more color. So here it flows either lambda plus infinity or lambda minus infinity. And for plus infinity, you have the charge density wave state. And here, let's call it the valence bond solid. So there are 3 phases in this global phase diagram: the Luttinger liquid, the charge density wave, and the valence bond solid. You're seeing a lot of similarities to bosons and half filling in 2 dimensions, except here there's no Z2 spin liquid. That doesn't exist in 1+1 dimension. And the Luttinger liquid is somewhat like a superfluid phase, as we're going to discuss in the little time remaining. Okay, so that's all correct. What this simple picture that I presented doesn't work when you get very close to K. So let me just show you without proof what the flows look like when you're close to the critical point. Then it turns out that then these are the famous Kosterlitz-Thouless flows. You actually have some what are called separatrix that don't go vertically, but at some angle. So now if I look at the flows, what they look like is the following. They're not vertical. So the flows here, okay, that looks fine here. But then as you get closer, they kind of turn in like this. And then for the purple side, they turn out like this. And then you get a whole new set of flows where lambda is large, but K is close to 1/2, which I'll draw with this. Well, those are really purple flows. They are flows that go like this. So everywhere there is a purple flow, you have either a charge density wave or a valence bond solid. Everywhere there's a blue flow, you have a Luttinger liquid. And it's all controlled by this famous Kosterlitz-Thouless critical point here in the center. Okay. And it was Kosterlitz who first worked on these flows, and that's presumably why he got the Nobel Prize a few years ago. So that's a correction to this very simple flow that I've written down here. The very simple flow is only hold at the ends of this phase diagram. And to identify that point at the center with the x at k equals 1/2, that requires more subtle calculation. We'll probably cover that at some point in the course. It appears in so many different contexts anytime you're looking at field theories in 2 space-time or space dimensions. All right, so that's it for fermions, spinless fermions with strong and weak interactions. So now in the remaining 15 minutes, I do want to finish this. I want to say something about bosons with strong and weak interactions in 1 dimension. These are ordinary bosons. I don't know what this IS is here. It's probably a typo. Okay. Okay, so we're considering some Bose gas. Let's imagine the Bose-Hubbard model with some 2-body interaction. If you take V naught as delta of x, then that would be the representation in the continuum in equation 69 of the Bose gas. So here are a bunch of bosons floating around, and what we expect generally at generic density, the boson will condense and form a superfluid. So this is some gapless phase. And now we want to explore the idea that this gapless phase is in fact nothing but the Luttinger liquid. And we'll see that whole procedure sort of makes sense. So one way to justify this, if you wish, this is, because you studied fermions so hard, we don't need to go this way, but since we studied fermions, let's imagine we can understand bosons once we studied fermions. So in 1D, there's a very simple way to take any wave function of n particles, which we call psi b, and convert it to a wave function for fermions of n particles. Any state can go from one to the other just by this this factor, sine of xi minus xj. So if this state is interchanged, is anti-symmetric under interchange, and so the combination will be symmetric. Of course, there's one caveat here is we have a hardcore repulsion that, with fermions, you can never have two fermions on the same site. And so we are assuming the bosons also never really want to occupy the same site. So that turns out to be a rather mild assumption. We don't, you can actually even carry out this argument with allowing for double occupancy by some canonical transformations. But let's not go all the way there. Okay. And this particular transformation from one wave function to the other, you can rewrite by what's called the Jordan-Wigner transformation, where the fermion field, psi b of x, is related to the other way around. The boson field is related to the fermion field by this phase factor. And this is a phase factor actually we have met before. This is a phase factor that gives you a -1 for every fermion that's to your left. So if you take the fermion field and you put this extra phase factor, which is essentially this factor in second quantized form, you will convert a commuting operator to an anti-commutating operator, or actually the other way around, the way I've written it. Okay. So therefore, let's just keep going in the same vein. So now let's assume that the fermion field is described by a Luttinger liquid. Okay, so what would the Bose field be described by? Well, all we have to do is take our expression for the fermion field and on the right-hand side, and rewrite the right-hand side using the theta and phi of the Luttinger liquid. So if you do that, it turns out to be, this is exactly the type of argument we went through last time. So I won't belabor it. You can read the notes. It's completely clearly spelled out. The leading term, instead of being e to the I theta plus phi at 2kfx, so maybe I should remind you. So what we found for the fermion field, where did it go? Well, I'll write it out. Okay. I should be able to get it right up to signs here. So for the fermion field, you recall, we had in this space here, we had psi f of x was the leading important terms was psi right of x, which was e to the I theta plus phi times e to the I kfx plus e psi left of x, which is what? Which is e to the I theta minus phi or something like that. I don't remember. Or is it phi minus theta? One of those two. E to the minus I kfx. And then many other terms. Well, so we insert this in here. And then for this, well, this is easy. This is just the integral of the fermions from -infinity to 0. That we know is just e to the I phi of x, or e to the minus I phi of x. Minus I phi. Because the density is the gradient of phi, you integrate it, you get phi. And so when the dust settles, the phi cancels here, assuming all the signs work out. And then the answer is very simple. We ignore all these higher order oscillating terms. And the important answer is that the Bose field is e to the I theta. So we have bosons at some density. Then, they want to Bose condense. And that Bose condensate has a phase. And now we know what the theta is. The theta is just the phase of that condensate, e to the I theta. Okay, and the low energy theory for theta is just d mu theta squared, the relativistic form, and that's the theory we met. When we in the second chapter of the course we did a Bose condensate and we looked at the phase fluctuations of the condensate in any dimension, and we found the theory was d mu theta squared. Okay. But now the big difference here in 1D is that theory d mu theta squared does not imply long range order. What it implies, if you work it out, and we just worked it out, in fact, for phi, and you do the same thing for theta, you get this very important result that you have what's called quasi long range order. There's no condensate, but the correlations decay with the power law. And the action here for theta, and if I think I even we're going to put Vf equals 1 was dx d tau, d tau theta squared. Okay, maybe I won't put Vf squared dx theta squared. Now this is, precisely the action we met in the second chapter for massless, for the spin wave or the phonon mode, the density fluctuation in superfluid. And the coefficient, if you may still remember, was the superfluid stiffness or the helicity modulus. Okay, go back and look at the notes if you've forgotten. So what we see now in 2 dimensions is this number, this mysterious Luttinger parameter K is nothing but the helicity modulus. So we have this state of matter here with quasi long range order, which was really first established as a stable state of matter by Costas and Thouless, where there's no Bose condensate, but there's still a superfluid stiffness. There's still a helicity modulus. K is non-zero. And the long range order of the Bose condensate is replaced by the quasi long range order of the Luttinger liquid. In this case, it's being in 1 dimension at 0 temperature. If you go to 2 dimensions at finite temperature, then the same kind of theory applies actually. And so there is an analog of K there, which is in fact just the superfluid stiffness. And that's non-zero, and which means there is a Meissner effect, even though there's no Bose condensate. Okay, so that's a Bose gas at generic density. Questions? Okay, so now you can ask, what about Bose gases at other densities, at commensurate densities, just like we did for fermions? And here the analysis is very similar, except, the easy way to do this, you start from the continuum and you put in a weak periodic potential rather than putting in, the KFs to begin with and then thinking of scatterings within the KF. Now you do the same thing not in the tight binding limit, but more in the weak potential limit. But you get the same answers. So for example, you can put in a potential cosine 2gx times the density. And this is some interacting Bose gas. And it's the same thing. I mean, this thing will usually average to 0. So you use this expansion here for the Bose operator in terms of the Luttinger liquid operators. And then you ask, when do you get something that doesn't oscillate and therefore average to 0? And you find that only happens at some very special densities, where 2 pi times the density is the reciprocal lattice vector for this case. And so that precisely is integer densities. So in the simplest case, you get a transition from a Luttinger liquid to a modern insulator with no broken symmetry. That we knew already happened from a study of the Bose-Hubbard model in any dimension. But now this is described, if you just work out all the factors here, it's a cosine 2 phi, not a cosine 4 phi. And this means that, in fact, the ground state is non-degenerate. That's what you expect at integer filling, when the density has exactly 1 particle per unit of the unit cell of the periodic potential. So, the theory itself is very different, very much the same as for fermions at half filling, except that you have to put in a cosine 2 phi rather than a 4 phi. And that 2 makes, changes some of the numbers a bit, but the basic structure is the same. I'll leave it as an exercise to figure out how to do bosons at half filling. Then you have to consider higher order terms here, not this one, but higher order terms that will give you a cosine 4 phi term in that case, and therefore you can get a charge density wave or a valence bond solid, just like you got for fermions. Okay. So in the end, the phases of a Bose gas are pretty much the same as the phase of a spinless Fermi gas. They have essentially the same structure. What's different is the type of experiment where you remove the particle from the system. Then you have to remember whether you're moving an anti-commuting particle or a commuting particle, and that will give you different photo emission spectrum. But other than that, they are pretty much the same. And in fact, that's what kind of follows from this this sort of identity here between Bose functions and Fermi functions. Okay. And and there's lots of scope for homework problems on these issues, which I'll try to think of over the weekend. But it's all explained very nicely here, I think. I wrote the notes myself. Yeah, so what am I saying over here? Oh, one more thing I should, this is, I think, worth saying. But any questions so far on the discussion on the Bose gas? Okay, so now let me just go over this. So what we have found is that the transition from a superfluid to a mod insulator appears when this lambda term here flows to infinity, just like it did for the fermions. So there's some operator here, e to the 2i phi. What is this operator in the boson language? So this turns out to be something quite interesting. It's a vortex operator. And let me show you how that works. Okay. So, here you have some Bose system, or which I describe as this phase. So you have this phase in space. And, it's slowly varying here and there, like this. And then something, and this is, let's say this is time going this way. And then something happens. And then if I look at the phase over here, it's a little different. I mean, it's almost the same, but let me start doing this. It winds around once by 2 pi. Okay, yeah, that's not a very good picture, but here the phase just roughly fluctuates around the vertical position, and here it roughly fluctuates around the vertical position, but then there is a region here where it winds around. So if I draw the value of theta, maybe that's a better way to do it. So if I draw the value of theta in this region here, if this is theta, which is the phase of the condensate, this is x, then theta, well, let's just say it's sitting near some fixed value. Let's call it pi by, I don't know, call it 0. Okay. So theta here is basically fluctuating around 0. This is 0. Oops. But in this vortex configuration, theta is going to be doing much more interesting things. Here's theta as a function of x. So now theta is fluctuating around 0 for a while, but then it decides to take an excursion and then become near 2 pi. So here it's near 2 pi. Okay, now if I look far away from the center of the vortex, if I look here or here, theta is doing pretty much the same thing, because 2 pi is the same as 0. I mean, the Bose operator is e to the I theta, whether it's 2 pi or 0, I don't care. It's the same. But there's a difference between the top configuration and the bottom configuration, because there is this kink-like solution where you have a domain wall and going from 0 to 2 pi. So now if you imagine that as you were moving in space-time, so you really have to think in space-time now, theta was flat, 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 and then at some point it became like this. Well, that requires a non-local change of variable. So there's some point in space-time, and some point in space-time then, there's a special operator, which we'll call the vortex operator. It has some spread, which changes you from no winding to winding. Okay, and now I'm going to make a claim, which is not totally obvious. But if you now take the space-time phase diagram of this configuration, this is x and this is time, that you can distort this configuration here smoothly to where you have no winding to where you have winding, with the vortex operator in between, is smoothly the same as what you might expect naively of what a vortex looks like. Is the same as this thing. Okay. So here you have a more realistic picture of what a vortex looks like. It's just like we saw in the Abrikosov vortex here, although there's no magnetic field. Okay, so this is the configuration of theta as a function of x and tau. And my claim is that the theta of x and tau in this space-time diagram in red is smoothly connected to the theta of x and tau in this purple diagram. They're basically the same. You can kind of unwind it so that there's all the winding. Here, the winding is is symmetrically distributed around the core of the vortex, which is really what it actually do. But here I'm thinking of the winding as, in a constant spatial structures and seeing the winding number along the spatial direction. Okay, so you can think of a vortex as a tunneling operator that takes you from no winding to some winding. Let's just say that's the definition we need. And just for your intellectual satisfaction, I'm telling you it's the same as that. I don't really need that. Okay, so now we know what a vortex is. A vortex is some operator. So I can just write down a vortex operator. Okay, it's equal to an operator, which is shift theta shift the value of theta by 2 pi for all y less than x. So that would be, well, okay, this is for y greater than x. So if you want y greater than x, I'll write y greater than x. But this is exactly the kind of operator we met last time, where we were shifting phi to get a density, and here you're just shifting theta. So how do we shift? Well, that's easy. You just take the canonical conjugate momentum. I'm not going to get any sign right here. It's I times beta of y, and you integrate from x to infinity of dy. And we also know that pi theta, and you have to shift it by 2 pi here. And we know that pi theta is 1 over pi times grad phi. Okay, so if we just work this out, you get the result claimed here, that e to the 2i phi is the vortex operator. Okay, this is the important statement. So what we are seeing here, and this will now make the connection to Kosterlitz-Thouless picture very clear. What we are seeing is that you have the Luttinger liquid, and the Luttinger liquid can have these fluctuations in space-time where vortices appear. These are so-called instantons. They're tunneling events where suddenly the winding number in some region of space-time is changing. So these vortices can appear, and in fact, they'll tend to appear in in pairs, and that's also something that this theory tells you when you work out its dynamics. Here we're just saying that there's some operator which creates a vortex at some point. It's a highly non-local operator in terms of theta, but the beauty of Luttinger liquid theory is you can just write non-local operators in theta in terms of local operators in phi, and vice versa. So that's the power of what we're doing here. So these vortices, vortex, anti-vortex fluctuations appear. E to the 2i phi is a vortex, e to the minus 2i phi is an anti-vortex, and they all start appearing. And now the interpretation of the RG is there's some region where these vortices just disappear. There are very few of them. And that's the Luttinger liquid. That's the superfluid phase, or the quasi-superfluid, if you want to call it that. And there's another phase that the vortices just are all over the place, and that's the Mott insulator. This is the physics of the costless transition from a vortex bound phase to a vortex deconfined phase. And it's just very nicely described by this very simple field theory here. The Sine-Gordon field theory in this language has the interpretation as a vortex deconfinement transition. Okay, I've gone way over in time, but that's the end of the chapter on Luttinger liquids. And any more questions? And of course, we'll continue our discussion tomorrow morning. Any questions? Okay, sorry for going over. And if you had to leave, that's fine. You can watch the recording, and please come to our discussion tomorrow morning.
Thank you.
Thank you.